All right, let's get started. Sorry for the little delay there. So today we'll do the midterm review, and I want to cover a couple of slides we missed last time on the discrete transform, which will be important. So the midterm is on Tuesday, so after the weekend. The solution sets for this exam should be available soon after that. And then we'll have that midterm retake, which will be the Thursday after fall break. So you go away from fall break, that's the Monday and Tuesday, and then that Thursday of that week, that's when we'll have that retake. So that means that, so you'll have the midterm on Tuesday, we'll have another lecture on Thursday, a week from today, then there's fall break, and then there'll be the retake. So between the midterm and the retake, you should at least see the solution sets for the midterm. And if the Scantron comes back quickly enough, you should maybe be able to see, even be able to see how well you did. And then if I might be able to post which questions that you had issues with, because it comes back to me in a nice format like that, but I just kind of have to restructure it and make it, anonymizable. But hopefully I'll be able to get that back to you before then the retake. And then the retake will be a different exam, but it'll be over the same content. It'll be very similar in format, but it will. So if you've studied for the midterm, I'm pretty confident that the same sort of studying will be adequate for the retake and vice versa. So that's the plan moving forward. There are a bunch of midterm resources on Canvas, and so I've posted 3 sample midterms and their solution sets. 2 of them are from back before I started using Scantron, and 1 is a Scantron example. There are the homework solution sets are on Canvas, or at least the D2 solution set will be available by this weekend, because D2 is I think, whenever D2 is due, it's immediately shows up the minute after the D2 window closes. And then there's now the ICAF was due before, which is like a practice ICA over all the pre-midterm material. It was due before this lecture, but once it disappeared, a new ICA that's a practice ICA, ICAF practice, showed up. And that is identical to ICAF, it just doesn't count for any points. But it'll still score you, but your scores just don't get put into the grade book. And so you can take that as many times as you want. And then if, this is kind of an older version of the Canvas, so it looks a little different now, but on Canvas, all the lectures are associated with book chapters. And so if there is any, if there's something in, say, lecture B1 that it still seems murky, then look in chapter 3, and maybe the way the book authors have put it together will be a little more clear. And of course, I've tried my best to do the audio and the video of every lecture. All those are up on Canvas as well, in case you want to review those lectures. So we've got a lot of material there, and hopefully everybody's going to feel prepped, and there'll be no surprises when the midterm comes up. So before I cover the couple of slides we missed, are there any questions about the scheduling moving forward? Midterms in this classroom at this time at normal lecture time. All right, so the stuff we missed, we were talking about the inverse transform method, and we covered all the continuous transforms. So like this exponential here, you know that, well, if you solve for the CDF of an exponential and invert it, you can then turn a uniformly distributed random number into an exponential just by running it through the inverse, or the quantile function of the inverse CDF here. And so the question is, well, what if I have a discrete distribution that I would like to sample from? And so a discrete distribution very often will be given by just its probability mass function. Well, we're going to do the analogous transformation for the discrete case. And so you have the PMF. So the first thing we need is the CDF. And so we convert a PMF to a CDF. So on a midterm, I could give you a PMF and ask you to sample from, I might, as you can see, I think I've done examples of this on previous midterms where I'll give someone a random number from 0 to 1, and I'll say, assuming this was your random number that Excel or Arena gave you, you build a formula that would give you a replicate that is consistent with this probability mass function using the inverse transform method. And then I'll be looking for the right outcome. And so your answers will either be a 1, 2, or a 3. So you get a number like 0.34, and then you have to figure out, do I want to answer a 1, 2, or a 3 for this 0.34 input? So how do I do that mapping? So the first thing you do is generate the CDF, and you just do that by adding up all the PMFs in a cumulative fashion. So you start out with 0.2, you add 0.5 to it to get 0.7, you add 0.3 to it to get 1. And then from there, that's going to end up setting up these cut points that tell us where to group certain random numbers with certain outcomes. So visually what's going on here is this is our graphical depiction of the CDF. Here's our 3 outcomes here. And here are the probabilities, the cumulative probabilities associated with each outcome, 0.2, 0.7, and 1. So reading straight up here, I just have the CDF. And so I start with that discrete CDF, and then if I was doing this on paper, then I would technically invert it. And so graphically, all I did was just switch the axes. I just imagine there's an axis going through the diagonal, and I just rotate it around that. So if I go back, it looks like this. Then I'm going to flip it this way. So that it flips up like that, so that now my independent variable is this draw. And if I just go up here, then I can end up seeing that, well, if I draw a point whatever, a point, say, 6, then it goes up and it hits this curve here, which maps to outcome 2. So that, 0.54, I guess, is the outcome that I drew in this example. And so, so that is kind of graphically what's going on there. Now, so this CDF gives you the boundaries for transforming this. So basically, this shows you that anything from 0 to 0.2 would go to an outcome 1. Anything from 0.2 to 0.7 would go to outcome 2. Anything from 0.7 to 1 would go to outcome 3. And then that will end up generating them with the right probabilities, because this has got, we wanted outcome 2 to be most frequent, and that's got the biggest interval. And so that's how that works. So if I want to see that not graphically, so how would I do it sort of mathematically, then I can set up these cut points as these inequalities here. And I basically just write the CDF down here, and I say anything from 0 to the first spot in the CDF gets that first outcome. Anything from that spot to the next spot in the CDF gets the next outcome, and anything from that spot to the end gets the third outcome. So I've just taken these CDF values here, and I've written them down this way to create those intervals that I showed you graphically. Like I said, it just creates these kind of cut points here. And then in Arena, if you ever wanted to do that, rather than implementing this logic manually, they have this convenient function called disc, short for discrete. And actually, you can type in the whole word discrete, and that works as well. And if you look at it, it actually is encoding the inverse CDF in its arguments here. So the first argument is a probability, the second argument is an outcome. Then a probability and an outcome, a probability and an outcome. So it's the inverse CDF, or if you prefer, it's just the CDF with the arguments switched. So I've got all my outcomes on the even arguments and all the corresponding CDF probabilities on the odd arguments. And this, if you encode, if I put this example into Arena in an expression somewhere, like let's say the expression is figuring out the number of customers who've arrived, or maybe it's figuring out the service time for a particular order. And I know that those service times, well, there's only really 3 service times we care about, but this one happens more frequently than the other 2. Well, I can just encode this in that C's delay release as the delay, and it will then draw outcome 2 more frequently, 50% of the time, but it will occasionally draw outcomes 3 and outcomes 1 as well. So you should become familiar with this, and it wouldn't surprise me if on a midterm, I haven't written the midterm yet, but there would be questions that maybe have, that make sure that you're familiar with this notation, so that you know that, that you can go from a CDF into Arena and back. And so a big thing to note here, a lot of people get confused by this disk function because they think that these are the mass functions. They think it's encoding the PMF, but the disk is encoding the CDF. So all of these probabilities have to increase. It has to go 0.2, 0.71. It can't go 0.2, 0.5, 0.3. If you tried to do that, Arena would give you an error saying that you have to be monotonic. They also always have to end in 1. Now, you sometimes get an odd argument out here. So sometimes you'll see comma 3, and then something else. Does anybody remember what that extra argument is with any of these random functions in Arena? I think I heard someone say it. It's the seed or the stream identifier. So in Arena, you can define streams, and each stream can have its own seed and random number configuration. And so you can tack on right to the end of this the stream, but if you don't do that, it defaults to 10. So, so if you do ever see a disk here and it has an odd number of arguments, that's because the last argument, the odd man out here, is that stream identifier. All right. So any questions about this, about how you could go from a probability mass function to an outcome, and how you might encode that in ARENA so that it can do this process for you? Okay. All right, so we can use that disk function and this sort of this general process to actually help us work with data that even when the data are not discretely described, so even when the data do not necessarily come from a discrete distribution, we can still approximate them by a discrete distribution, and that ends up making it more convenient for us to sample from something we're not quite sure what the real continuous distribution is. And let me get, make that a little clearer here. So we've already, when we talked about the Kolmogorov-Smirnov test, I introduced this phrase, empirical cumulative distribution function, or the empirical CDF, otherwise known as the sample CDF. And I said that the sample CDF, you get it from taking, let's say I had capital N number of samples, and I just sort them so the indices are always in this order. So this isn't the first data point I sampled, this is the lowest in the set, and this is the highest in the set. And then after I sort them, I then can create a function, or basically create a graph, which maps every outcome to its position in the list divided by the length of the list. And this here will end up having all of the properties that we need of a discrete CDF. And so as an example here, you can kind of view this as I've got all of these outcomes over here, and even if we know it's drawn from a continuous distribution, as far as we know from the data, it might as well have been a really, really fine-grained discrete distribution that only had these outcomes in its probability mass function. And we can associate with each one of those 1 over capital N probability mass. It's like uniform distribution across these discrete outcomes. And then that would give us this cumulative distribution where it's hard to read 1 over capital N, 2 over capital N, I over capital N, all the way up to N over capital N, or 1. And so this is one way we can approximate these data that we came in as a discrete distribution, even if it's not really discrete. And the benefit of that is that now, if we were to plot this, so these are data I brought in, and as far as I know, these came from a continuous distribution, but after I sampled from the data, let's say I wasn't really sure what continuous distribution it was going to use, and I didn't know how to fit one, or I just didn't really have a good fit. Well, then I need to go somewhere, so I'd say at least for my prototype simulation, I want to just sample from a discrete distribution that uses these outcomes, so at least I get the same outcomes that I got in my data with the same frequency that I got in my data. And that's what this is representing here, this empirical CDF. And so with this empirical CDF, I can still draw a number between 0 and 1 and map it to an outcome. Question?
Could you repeat real quick how did you read, like for when you do the inverse transform for discrete BMFs?
How you read them?
Yeah, like how would you...
Like the meaning of this graph? Is that,
yes.
Yeah. So yeah, down here, these are all of the possible outcomes, and they jump up. So outcomes that have probability mass at them correspond to these steps. So of course, I've only written out on the axes the outcomes that occurred here, but outcome 0.1 is here, but it's flat, so it doesn't have any probability mass associated with it. So every time you get a step, the step is actually proportional to the probability mass. In this case, all the steps are of equal height because I'm saying that I only saw one of each one of these in my data set, so I'm uniformly distributing probability over these 5 values. But if I saw 0.25, say 4 times in the data set, this step would be much higher. Question?
So yeah, when you're doing the discrete transformation, so it's literally just you flip to have the inverse transform.
Yeah, in all of these, graphically, that's all you do is I guess regardless of discrete or continuous, if you had pairs, you just flip the order of the pairs. If you had a graph, you just flip the axes. The difficulty, as you did on the homework in homework D2, was when you want to then analytically solve for a function that matches this graph. That's when you have to go into maybe a little bit extra effort. But if you have the graph, and you have a mechanism for doing this all graphically, then if you just flip everything, then you're done. So, does that answer this clear about what the empirical CDF is, the outcomes down here, and then the probabilities, the frequency of those outcomes accumulated here. So now that I've generated this sample CDF, if I draw a random number between 0 and 1, I do the same trick I've been doing for everything else. I just say, which outcome is, that if I were to sample here, which outcome does that map to? And so anything between 0.4 and 0.6 is going to map to 0.4 on this. Anything between 0.2 and 0.4 is going to map to 0.35. Anything between 0 and 0.2 is going to map to 0.25. And so this gives me a way of generating simulated data that matches the proportions of the data in my real sample set without even coming up with a curve fit. And so the outcome will end up looking like this. So I took these data and I put them into a disk line just like the one that I showed you before. So this disk line in general is going to look like this down here, where I've got the probability 1 over n, comma the outcome, comma 2 over n, comma the outcome, all the way up to 1.0, comma the outcome. And so if I then had ARENA generated a lot of these, then I would end up getting a histogram that might look like this. Or maybe, in this case, all of these, this is a sort of a small sample set, but if I did have samples that were more frequent than others, then some of these bars would be a lot higher than others. But, yeah, question?
It's a kind of small question, but which order does it include, like in the 1 over n in your CDF? Does it include like the first order, the second order?
You mean like if I drew a
Does it
0.2?
go all the way to 0.25, or does it include like up to like less than 0.25?
Does it include, I guess,
Sorry, like on the x-axis, otherwise does it go all the way to 0.2, or is it like everything up to 0.2?
I would say that if you drew a point, it actually doesn't matter if you drew a 0.2 exactly, but everything from 0 to, and then the open interval 0.2 will end up mapping to 0.25, and then I would say from 0.2 to the open interval of 0.4 would map to 0.35 and so on. But it turns out that what you do with these individual points, it doesn't matter in the end because they happen with 0 probability. But yeah, so, and I won't ever ask you a question on a boundary. Like that would just be a trick question. All right. So yeah, discrete. Was there another question? And so this is what you would end up getting: simulated data out. So I measured these data. I asked ARENA to generate samples from a distribution matching these proportions, and it gave me these 5 values out. Now the downside of this is I said, well, you know, that's technically what I asked for, but I really want this to approximate a continuous distribution that just happens to sort of show these outcomes with the same proportionality that they had here, but I still want other outcomes. Like if I'm approximating a continuous distribution and I've only looked at a small sample set, this would not be a good approximation of a continuous distribution because I would never get values in between here. When I would just, if I only took a couple of data points, I was just unlucky to never get them in between here. So one option, if you can't take more data, is ARENA gives another command called cont, C-O-N-T for continuous. And it has exactly the same format as disk, but it interpolates in the CDF between each one of these points. So before, if I go back, the CDF had all these stair steps. So all this cont function is doing is it's drawing a line between all these corners here to generate a continuous distribution. And still, at every corner, that each one of these outcomes at each one of these corners will have the same proportionality that it did in the real data set. But now it will throw in additional points in between that are consistent with that. And what sometimes you see done here is, if you notice when I go to the disk, I start with 1 over n. But in the continuous one, if I started with that 1 over n, which I can do, it ends up basically making this outcome be the minimum outcome, and there's like a huge probability mass that's sitting on top of the minimum outcome, and then everything else gets smoothly spread out over all of these other outcomes. And that's often not desirable. So if you have a priori information that you should expect a different minimum, like let's say 0.25 is the minimum I saw in my data, but I'm pretty sure I could have gotten all the way down to 0, then I can start my count out with 0, that hypothetical minimum. And then that will end up putting this line down here, and then that gives me a smooth distribution all the way from 0 up to my maximum value of 0.95. But it has these kind of funny steps in the P, it's an approximation of probability mass function, because it's sort of uniformly interpolating between these outcomes. So it's the difference, and in other words, it's just putting straight lines in the CDF. So that's disk and cont. Cont is just a way to smooth out disk if all you have is a small number of data points that you assume are from a continuous distribution, but you don't have any way of fitting it to a known continuous distribution that you could otherwise generate with an inverse transform. Questions on that? All right, and then so there's one other case, is that sometimes we do have nice formulas for discrete random variables. As an example, the geometric distribution, if you don't remember what the geometric distribution is, it's a random variable, which is the number of, if I've got a number of coin flips, of weighted coin flips, my question is, how many coin flips do I need for a certain number of successes? So I would like to see 5 heads. How many coin flips do I have to flip with a fair coin or with a maybe 75% heads coin in order for me to see 5 heads eventually? And that's what this PMF gives us, and this is what the CDF gives us, and this is the plot of the CDF. So we've got these two, and so graphically, of course, I could still do this, but if I think about it mathematically, I've got a way in which I can encapsulate that in a much more elegant form. I know the formulas for each one of these stair steps. And so I can say what I really want is the outcome K that sandwiches the random number that I grabbed between the CDF at outcome K and the CDF at the next outcome. So I can see my CDF here, f of K is 1 minus 1 minus P to the K plus 1, so that's what showed up here. Plugged in K here, I plugged in K plus 1 here. And now I can, in theory, I should be able to solve these two equations, this equation and that equation, simultaneously, and to get an idea of what bounds I have on R that correspond to each outcome K, and I have a nice closed form expression. So if I do that, then I end up getting, so if I solve both of these simultaneously, I end up getting something that looks like this. And if you look closely at this thing, this is saying, if you keep in mind that K has to be an integer, then I'm saying I need to find the integer that fits within these two bounds, and I can use the ceiling function to represent exactly what's going on here. So this, if you've never seen this before, this operator, so this thing that kind of looks like an absolute value, but it has a little hat on both sides, that's the ceiling, which is the smallest integer that is at least as big as the thing inside the operator. So the ceiling. And so then I end up getting, I take my R that I calculated, that I got from my random number generator, I plug it into this formula, which gives me some number on the real line, and then I end up taking the integer that is at the smallest integer that is least as large as that number, and that will be my geometric outcome. And if you look closely at this, you may notice that this is similar to the exponential random number generator. So if you remember that P is a constant, your exponential random variate generator that you use, let's say on the ICAs you've used it, then that, and we talked about it last time, that has a natural log 1 minus R, and then it has a mean out front. Well, that mean is just a constant, and so is this just a constant. So this looks like a discrete version of the exponential, which makes sense because if you look at this formula here, then you can kind of think of this as you've got these probabilities that keep multiplying, Or if you even think of it conceptually, it's the time until, like let's say if I say that the time until the first failure, well that's like a waiting time distribution. So this is like the discrete version of an exponential waiting time. So it's kind of not surprising that I'm just quantizing what is effectively an exponential random number generator. So that's why it's not sort of a mistake that that looks just like the exponential. But not all of these random variate generators that you use will end up looking this way. It's just the reason it looks that way is it's effectively the discrete version of an exponential. It is also memoryless, for example. But the thing I might want you to focus on is, in principle, if I gave you a formula for the CDF, you could set up a similar sandwich inequality like this and then solve it to end up generating an inverse transform generator that has a nice closed form for a discrete outcome. All right, any questions about that? Which kind of concludes our discrete inverse transform. All right, so if you wanted to implement this in Arena, Arena doesn't have a ceiling function, but it has this int function, which is like, it basically is a rounding function. It finds the closest integer. So if you want to implement ceiling, what I do is just to add 0.5 to the argument and then do int around that. So this int 0.5 plus is effectively the ceiling, and that's what's inside the ceiling. So that is a way that we can generate geometric random variables inside Arena without having to manually put in every probability into the disk function. Questions? Or no?
Yeah, actually, so where did that 5 come from?
Yeah, so with the int function, it's like the nearest integer, and if I don't want the nearest integer, I want the integer that is at least, I want the smallest integer that is at least as big as this thing. So by adding 0.5, if I'm, that sort of forces that. Any other questions? All right, so the big takeaway from that lecture, and so I'm skipping a lot of this kind of, I mentioned, I said if you couldn't sleep at night because you're afraid of what happens if I don't have an inverse CDF, if it's not possible to solve, I said there are ways to deal with that, and we don't go over those. I put extra slides on that in case there were time for just sort of for information's sake. In more advanced classes, like, I don't know, IEE 545, you might end up like actually going into how to say sample from a normal. We all very often sample from a normal distribution, and fortunately, Arena gives us a function that already does that. But if you actually want to ask how do you sample from a normal, that's very complicated because the CDF of a normal, although we know how to write that, the inverse CDF of a normal does not have a closed form expression. So you cannot use the inverse transform method directly with a normal distribution. So we have to come up with other ways to sample from a normal. Same with a gamma, a beta, a bunch of other common distributions. And there are ways to do that. They're just kind of outside of the scope of this class. But just know that these things exist. And then also, if once we can sample from a normal, one of the cool things we can do that's very difficult to do with other distributions is we can create correlated random numbers. So we could say, what if I want my inter-arrival time to be correlated with my service time? In other words, the longer you wait for someone to arrive, the longer they're probably going to take in service. If you have a system that you believe that's the case, and you want those two things to be correlated, then the question is, how do I manage to draw from two distributions and ensure that there's maybe a 60% correlation between them? Well, it turns out it's very easy to do that only if you have two normal random variables. You can mix them arithmetically and get that correlation. But it's difficult to do that with any other random variables. And so there is a method called the normal to anything, or NORTA method, where you can take two correlated normals and turn them into two correlated anything else's. So that's where that normal to anything. And so in more advanced simulation methods, whereas we focus primarily on inverse transform, they use the inverse transform to build up to the NORTA. And then you use the NORTA for like everything, because in those cases you might actually have to be forced to build those correlations. So, these methods do also exist. But fortunately, Arena has done a lot of this work for us for the common ones. And if you have approximations of other distributions that arena doesn't have, you've always got disk and con that you can lean on. All right, so any questions about the discrete sampling stuff before we go into the midterm review? All right, so the midterm review, just as a reminder here, and then I'll take questions or go through slides. Oh, yeah, question?
I actually have something unrelated. So on the first homework, it grades 30 out of 35, counting the bonus as part of the points.
Oh, okay. Well, then I thanks for mentioning that. I'll go and
Okay.
fix that.
Yeah.
Okay. So that was apparently a Canvas mistake, but I can take care of that. Okay, so the midterm retake, they're both here, but one's about a week and a half after the other one. Both of them are going to be closed book and closed notes. On both of them, you can have two-sided handwritten formula sheets. I say handwritten. If you really want to, type it up or something, that's fine. But when we look at your formula sheet, it shouldn't have anything photocopied out of a homework, out of a book, or whatever. You can hand copy something out of a homework, that's fine. But we want to force you to recreate it, either by typing or by writing. No need to copy numbers from the back of the book, chi-squared tables, KS, that sort of thing. I will give you tables of numbers. If there's formulas that you think you might like the linear congruential generator, that's like a good thing to put in your formula sheet. Exam will have an A and a B version, and I'm almost definitely going to be using Scantron for this. I'll bring a box of number 2 pencils. It's good if you have your own pencil too. If you do with the Scantron and pen, it just gets returned to me and I have to hand grade it. And so I don't guarantee that I will hand grade it. So bring a pencil or use a pencil that I provide. Something that I guess a lot of other people don't do, but I really like to do, is to make use of the multiple bubble answers. And so sometimes I'll say select all, or sometimes I'll give you more than 5 options. And then so you'll not only have A, B, C, D, and E, but you'll have AB and AC and AD. I mean, I can imagine lots of combinations. So I can give you a huge list that I can encode in 5 bubbles. And so, but then people then ask, do I really just bubble more than one? And yes, you do. I can also ask OR questions. So be prepared for those. Don't be surprised if you see those. Every question will be 1 point. So there's no partial credit. So you might spend 5 minutes doing a math problem and then bubbling one thing, or you might spend 10 seconds, doing a concept question. And the rationale I have for this, although I will try to break quantitative ones up into maybe multiple questions, which is kind of a discrete approximation of partial credit. But the rationale here is, as much as we want you to do chi-squared tests by hand in class, all of you know you're never going to do a chi-squared by hand ever again. And likewise, in a job interview, no one's going to ask you to do a chi-squared by hand. Well, they might, but that's just because they're bored. But what they might ask you is, what statistical test would you use if? And it's those concept questions that I think are the ones that are more valued, because there always are tools that can do the quantitative stuff for you. So we want you to know how to do the quantitative stuff, but leaving this class, you're not seniors, you'll be seniors soon. We want to make sure that the concept stuff is really solidified. So that's why, even though you might think, you just asked me, if something is an exponential or a Poisson, and I bubbled an exponential, that doesn't seem like the same amount of work as solving a runs test. But to me, it's just as important. And then the exam is worth 20% of your course grade, and then you're going to take the highest of these two. If you don't want to come to one, that's fine. Just get a 0 for it, and then your grade will be the other one. Any questions about the format or anything? The inspiration for my questions that maybe today that I'll put together is basically this. So there's going to be a bunch of multiple choice questions where I'm going to ask about concepts, DES, pseudorandom number generators, probability distributions, which one does this, which one does that. Very basic arena expressions, disk, cont, things like that. Definition-related fill-in-the-blank questions, picking the name of tests, maybe some simple calculations. I might show you a hand simulation, but it'll have gaps in it, and you'll have to maybe fill in those gaps. I might show you some graphs of PDFs and CDFs, which one is the PDF, which one is the CDF. And then I'm going to give you number sequences and say which one of these clearly violates the independence property, something like that. Numerical problems. So a couple of these where maybe you have to do a small, like 4 or 5 lines, maybe just 4 lines of a DES by hand, and then I'll ask you for some cumulative statistic that you'll only get right if you've done all of those lines. Or maybe I'll ask you to generate a sequence of random numbers, and I'll ask you for the 5th in that sequence. Or maybe I'll have you do statistical tests of uniformity or independence using either chi-squared or KS or the runs test. And then the design problems, so definitely expect to have to design a continuous random variate generator and maybe a discrete random variate generator. I think on the sample that I gave from last semester, I asked people to do both. So I have a tiny discrete random variate generator problem and then a little larger continuous random variate generator problem. I probably won't ask you to do both the integration and the inversion all in one step. That way you don't mess up one. But I probably might ask you something, I could ask you to, integrate to get the CDF in one question, and then I'll give you a CDF another question, and then ask you to turn that into an inverse transform in that question. And then again, the answer might be, well, here's a random number, tell me what the outcome would be with your generator. So questions about the format? Or just in general? Any questions? So from here on out, the way I've got this structured, and I don't have to do any of this. I can just switch to a tablet here and then take sort of notes on the board and post these after. Based on your questions, we can work problems or whatever. But the way I've got it structured is I've got kind of feedback from the 3 homeworks, just kind of common problems and common solutions, things to look out for, and then a review of and this is meant to be kind of an inventory or almost a study guide of things that I think are the most important out of the lectures we've had so far. We don't have to get to any of that. If there are burning questions that any of you have, yeah.
Can we just do a quick example of how to do a discrete random generator?
Okay. So we can do that. So the question was, how to use a discrete random number, or how to build a discrete random generator. So let me bring up.
Wait, I'm just a little confused as to really what a discrete. So I know we just talked about that, but I'm just kind of confused about. Is that just like LCG? No, that's not.
Well, so LCG, so the linear convolutional generator, that's how to generate the UO1s. So the discrete random variate generator is if I were to give you, I might say that, here's an outcome. So I might say that here is a PMF. And I will say that, this outcome is going to have a 20% probability. And maybe this outcome, I'll call it 5, will have a 70% probability. And some other outcome, we'll say 10, has a whatever's left over, which I think is 10%. And I might then say that, every other outcome, if I forget to say this, I'll mean this. I'll say, so for all other x. So the idea here is I've got this, there's only 3 outcomes, and each one of them use up all of the probability. And then I might ask, all right, so generate a discrete random variate generator. So the way I would ask that on a multiple choice exam is I'd say, I might do something tricky, and I might give you a list of uniformly distributed random numbers. So I might say that there's you've got a uniformly distributed random variate generator that gave you this list of 0.14, 0.6, whatever. So you'd imagine a list of numbers between 0 and 1. And then I might say, working from left to right, generate a single, or maybe I'll say generate 2 or whatever, but I'll say generate a single random variate from the desired distribution up top there. So you would have to know that, all right, I need to then grab, Siri wants to help right now for some reason. So you would have to know that I am eventually going to plug this into my random variate generator. So then what does my random variate generator look like? Well, I'm not asking you to show your work, right, because I'm just a multiple choice test. So you could solve this in a number of different ways. The way I might solve this is just to say, well, I know if I were to write my cumulative distribution, so I'll do f of x, I could say, well, f of anything less than 1 is equal to 0. F of 1 is equal to 0.2. f of 5 is equal to 0.9, and f of 10 is equal to 1.0. And so then my question is, well, I guess I'll maybe ask you guys. So then the question here is, what do I do if I were to draw a 0.4? Which outcome would this correspond to? I heard a 0.2. Why do you say 0.2? No. Okay, so how? Okay, well, I was so we've got the outcomes here. So these are our outcomes. I'll highlight them maybe. So basically our choices for outcomes are these guys: 1, 5, and 10. Do 1. So 1. Why do you say 1?
Because it's in between 0 and 0.2.
There we go. Right. So here, if I look at this number here, 0.04, that falls within this interval. And so that means that it corresponds to that outcome, the next outcome. So if you were to write the CDF, you find where the random number falls, and then you go to the next outcome. So if I were to then say, okay, well, let's say I wanted to draw 2 random variates. Well, then I'd have to know, well, the next random variate is 0.6. So let's say I did say, okay, for r equal to 0.6, then what outcome corresponds to r equal to 0.6?
I
Yeah.
just have a
Okay.
question, and are the 1, 5, and the outcomes because you already switched the CDF, right? You already like inverted it.
Yeah, you can kind of think of me moving from right to left is the inverse CDF. From, yeah, you're right. So, any guesses? So if I drew r equals 0.6, and I wanted to generate an outcome consistent with an inverse transform, then what would the outcome be? 5. Okay, cool, great. So if I were to go to my highlighter here, and I'll say, okay, so this interval here, that's where that one goes into, and so that goes to that outcome. And so we could do this all day. But that's basically, I might give you more outcomes than that. I won't give you too many more, but the basic idea is you're just going to cut 0, 1 up. You're basically you're generating a number line, really. It's like the random dart method in the book. And so you're just going to take an interval from 0 to 1, and you're deciding on cut points that where each one of these is proportional to the probability mass of that particular outcome. And so you take the outcomes in order as that I give them to you, and you then create these cut points, and then you draw random numbers, and it's like the darts throwing in here, and then you see which side of the cut points they go on, and then that will tell you which outcome. So this outcome owns this space, this outcome owns this space, and so on. And that's just what we did here, but it's turned vertical. Any questions about that, about drawing from discrete random variables using this inverse transform method? And I'll post this PDF online after. Any other general, yeah, I'll take that question here.
Do we have to worry about numbers greater than 10?
Great. For this one, no. The only outcomes you worry about are these 3 here, 1, 5, and 10, because I've set up there that the probability mass is 0 everywhere else. So the only possible outcomes are 1, 5, and 10. Now I might give you, it's something arbitrary. It could give you, this could have been P of 1,000, and that would have been an outcome. But just for this one, you only have to worry about 1, 5, and 10. That makes sense?
Like if r was 0, it'd be 1 still.
That's right. Yeah.
So we won't have to do anything like on the homework where we were asked to build like a CDF for the.
Yes. So so this is the discrete. So that's the continuous one.
Yeah.
So definitely be able to, if I give you a probability density function, be able to generate a CDF. And if I give you a CDF, be able to invert the CDF to do the same thing here, to draw that, to be able to draw an outcome.
my question was actually for the discrete, will we have to be able to like build the inverse transform function?
Well, so I mean, the only case that I've shown you that is that case of like the geometric, where I could, so that geometric example would be one where it would be unlikely. I'm willing to say, as long as I'll take your word for it, that you will study that one slide that I had today on the geometric one where we've got an analytical expression, that's the one with the ceiling function for drawing these, then I won't put something like that on the exam. So all the discrete draws will be probably something like this, or they're not going to ask you about a formula with respect to the discrete draws. I could say, generate your inverse transform generator and then add up all the exponents, and then that will be your answer. And so that, so I could ask you about making sure you got the right formula for your inverse transform generator for the continuous one. But for the discrete one, because you have to do it kind of so rarely, I'm okay with you just kind of mastering this and focusing your efforts on this. Yeah.
For example, when you have square roots in
Good.
PDFs, when you're choosing like the sign for a square root, do you have to take care of the range of x, right?
That's right.
Okay.
That's right. Yeah, so that's a common problem, and you definitely would expect to see that on a midterm. If I give you, if I give you something like F, so I'm going to write something that won't actually be a CDF, just because I don't want to take the time to make sure it. Well, actually, maybe I can get it right. No, I'm not going to bother. But so if I were to say f of x is equal to, x squared, but it's only defined on the domain from 0 to infinity, then if I were to do an inverse transform of that, or well, let's say, I'll just make this easier. Actually, I can make it a real CDF. I'm going to make it just defined from 0 to 1. All right. Anybody off the top of their head know what CDF this is? All right. Okay, that's fine. So if this were the case here, so the reason I said this is a CDF because f of 0 is equal to 0 and f of 1 is equal to 1, and it's monotonically increasing between there. So it checks all our boxes for CDF. So if I wanted to invert this thing, well, the inverse of this algebraically looks easy. So I can just set r equal to x squared, and then I can solve, and I get x is equal to, and then there's that pesky minus square root of r. And I know that my r is going to be between 0 and 1. And so the question is, how do I make sure that my x is going to be in whatever the x range was? Now, here I said the x is defined between 0 and 1. And so I would then make the choice of saying, all right, so in that case, x is equal to the positive square root of r. But I could have also said, what if my f of x is also equal to x squared, but my outcomes go from -1 to 0? So now I'm saying that I have it happens to have the same formula for the CDF, but all my outcomes are negative, or we got this one, they're non-positive. And so here I could go through the same math, and I'm still stuck with this plus or minus question. And in this case, I have to choose the minus because I know that my outcomes are all negative. So you have to, the output of your random-variate generator has to produce outcomes that are in the kind of input of your CDF. So if your CDF is defined on negatives, then your outcomes out of your inverse transform better give you negatives. And this goes for the piecewise versions too. So if you're solving a tiny piece of the CDF, and that piece of the CDF has a bunch of negatives in it, then you need to make sure that you choose your square roots to generate those negatives. Now, it happened to be that the negative choice here corresponded to the -1 here, but algebraically, there could have been there might have been other things in this expression, and that might have made it like actually choosing the plus here is the thing that produces the negative. So you just have to think it through. Like if I chose a negative here, what would ultimately happen to x, and does that x land in the range that I want? Any questions about that? I saw that here first.
So that X is the original range from the CDF,
Mhm.
so you don't look at the new boundaries you come up with.
And well, in this case, they would be the same because it wasn't piecewise.
Yeah.
But if this was a piecewise CDF, so if I was like doing, if I had an f of x is equal to something, so it's going to be whatever x squared from negative 0.5 to 0, and then it'll be, something else. This won't necessarily be a CDF, but it'll be whatever 0.25 plus x squared from 0 to 0.5 or something like that. So in this case, I would have to say, well, all right, so I know that this top one, if I were to plug negative 0.5 into there, I can see that this top one maps to an R range from 0.25 to 0. And I've written these backwards just because I'm trying to map. The 0.5 goes to 0.25 and 0 goes to 0. And this bottom one maps to, so this is going to be 0.25. So again, this is going to fail as a CDF, but I'm just trying to demonstrate demonstrate how this works. So then the 0.5 goes into there, that becomes a 0.25, they add together, and this goes up to 0.5. So actually it still works the way I wanted it to work. But so this interval goes from 0 to 0.25, and that came from plugging in these values. This interval goes from 0.25 to 0.5, and that came from plugging in those values. And it is this x range that you have to choose your square roots to be consistent with when your R is in this range. Does that make sense? Yeah, question, go ahead. Well, there was a question. Yeah, there.
So, for the continuous case for the homework, how exactly do we get the confidence?
Okay, good. That's a good question. So I think let me flip back to the slides because I think I've got a canned example that if I do will be easier than me trying to come up with something. Oh, actually, the homework feedback will work for this too. Yeah. All right, so here is a simple example that is a real PMF and a real PDF or CDF. So I have this PDF, and the temptation is to integrate each piece. So I integrate under 0, I get, it's on auto, hold on. So I integrate under each piece, and if I integrate under 0, I get 0. If I integrate under 0.25, I get 0.25x. 1.5, 1.5x, 0, 0. That's the temptation. But it's wrong, it's incorrect as a CDF because it starts at 0 the way a CDF starts at, but it doesn't end at 1. So it should have a 1 down here in this box if we've done it correctly. So the question is, how do we add the constants in properly to make this work? And so the most general form of this is I say, you break these things up. And so let me try to make this a little more concrete. So for this top range here, from negative infinity to 0.5, that's this range here, I know that I'm just integrating under 0. So I take the integral from negative infinity to x under 0, where x goes up to 0.5. And so that's just going to give me a 0. Now, for this is where potentially you could get one of these constants out. For this range from 0.5 to 1.5, then I integrate under the original, this curve all the way up to 0.5, and then I start integrating under this curve from 0.5 all the way up to 1.5. And so in this case, the original curve just had 0 under it, so there's nothing out front. But this is where one of those constants could have gotten added in. So then now this integral I can take, and then that, I just have to remember how to properly integrate with limits. And so that's another place where these constants get added. Because if I just take the antiderivative, it's 0.25x. But once I put in those limits, then I get 0.25x minus 0.25 times 0.5. And so that's another place where those constants can come in. So the constants either are kicked down from the previous step, or they come out of using the limits of integration, where the limits of integration went from 0.5 to x. Well, there's the 0.5, and there's the x. So if you keep doing this process, then down here, you have all of those things combined. And so I've got my 0 from my first piece. The second piece here is if I integrate under 0.25 from 0.5 to 1.5, I get this, 0.25x, where x is 1.5, and then that 0.25, so this is that 0.25x evaluated at 1.5 minus 0.25x evaluated at 0.5. And then and that gives me this thing. And then I'm finally left with integrating this from 1.5 to x, and then that's going to introduce additional constants from the limits. And so you're constantly just accumulating, which is the point of a cumulative distribution function, accumulating all the prior constants and then adding in your own. Does that make sense? So just any other questions? Yeah.
Regarding random-variate generators, the reason why you're doing the whole procedure is basically because you can't pick just any value that you want for a random variable.
You have to go through the whole procedure because after modeling, you do a stochastic model, and it comes up, and you just come up with some PDF, some generic PDF that says, this is a model of demand in this inventory system, or this is a model of how people arrive to this restaurant. And that model, that stochastic model, may not look like anything that's just out of the textbook. It may not look like a normal distribution. It may have some arbitrarily shaped PDF. And so the question is, then how do I simulate, virtual entities that they'll behave according to that? And that's why we need these random-variate generators. And so it gives us a way to take any arbitrary PDF like this one that you've used your kind of stochastic operations research to build this PDF, all the sort of basic stuff you know about probability and modeling. You built the PDF, and now we have to solve for the CDF and invert the CDF so that the simulator can now draw outcomes that are according to this PDF. Yeah.
So when I plug in the values I got into Excel, most of the random variates I get are negative. Is that incorrect?
So without giving away the solution of the homework, it is not necessarily incorrect or correct. So basically the range of random variables could be anything. So it would be incorrect if you look at the PDF I gave you and you say the range of this PDF is positive, but I'm getting negative numbers out, then it would be incorrect. But if you look at this PDF, and so for this PDF, I can see that it's 0 all the way up to a positive number. So for this PDF, I should never get any negative numbers out by random variate generator. But for the PDF I gave you on the homework, and I don't remember it off the top of my head, if that PDF puts some density in the negative numbers, you better get negative numbers. Other questions? Okay. Well then, if other questions come up, I'm just going to flip through some of these things, and as we kind of marinate in them, if other questions come up, then just let me know and we can divert. But basically, if I jump back just to some quick feedback on the homework and problems that I'll see on the homework, but I'll also see on the midterm. Some of them are subtle, which is why I want to make sure at least mention them. Let's start there and go forward. All right, so so homework B1. Hopefully everybody feels comfortable about activities, delays, events. how they all relate together. If there are any questions about that, let me know. Just sort of just kind of a study guide here. So we can kind of get to some of the quantitative things here. Events, again, so be comfortable about the difference between an event and an activity, and how an activity always has an event at its start, an event at its end, but a delay is sort of the result of these activities stacking up funny. Getting to the quantitative stuff, if I ask you to generate random number generators, so always remember to divide by the modulus. So a lot of people, they'll generate the kind of internal workings of that random number generator, which will be like a 5-digit number, but then they'll forget to divide by 100,000 or 10,000 or whatever I give you the modulus is. And so, so make sure you divide by that. Also, if I give you a seed, if I ask you to like generate 5 random numbers, the first random number shouldn't be calculated directly from the seed. You should go through the process once, and then the first random number should be that first output. Because the seed we kind of know, and so it'd be easy, that's not really a random number. The random number comes from the arithmetic kind of being unpredictable in what it's going to produce next. And so the first number is the one you get from processing the seed, not from the seed itself. Other things, weird arithmetic things that come up just I think because we're not used to working with numbers that much. Like, at some point in our career, we work with all, variables, and then we forget, like, you just become unaccustomed to looking at numbers. And so we end up grading a lot of these things that finally people, they'll when they're comparing numbers, like in the back of the stats table, like I'll see this mistake come up with, like, they'll be comparing to 0.127, and they'll say that 0.127 is greater than 0.18, So, like, those are easy, like, by eye mistakes to make, and just be careful, not making them. Likewise, they'll get a lot of these like place value things where like 71 over 1,000, people drop the leading zero. So be careful about that. Just general ordering of place value issues. So I don't think that people don't remember how place value works. I just think that like you're working quickly and visually, so I kind of like just very quickly like, oh, okay, well, that's 18 and that's 127, and I'm just going to go. The degrees of freedom, remember that you actually have to look for the KS, you have to change the degrees of freedom with the number of data, and you also have to, whatever critical value I give you, the type 1 error rate, which it's always going to be 0.05 on the exam. I'm not going to change it because you think you're most accustomed to that, but the amount of data I give you could change. So even though you might have remembered 0.457 from an example you did, because I give you 6 data points, it might be 0.521 on the exam. So be careful about that. When you're answering these questions, so this was more for the homework, but don't just say we've rejected the null. Tell me what we've rejected. So then tell me the conclusion. Does that mean they're uniform? They're not uniform? What does it mean? Then the D2, we've already gone over the first, the bulk of this, which was that making the CDF. But then choosing intervals to invert, that's another thing that people sometimes have trouble with, but a good rule is that if the piece of the CDF is constant, it's not going to make a difference in the inversion. And you can just think of that graphically. If I'm mapping a random number on the y-axis, if there's a constant value, it's not going to hit anywhere. So we only care about where an x shows up or where you don't get a constant value. And so in this case, for this CDF, we only care about these middle 2 rows. These are the only ones we have to worry about inverting. And if we do it right, then we'll end up mapping this interval from 0.5 to 2 to the interval from 0 to 1. So the inverse CDF maps that interval back. And so when you end up doing this inverse, and so we've got this top one here. So we've already kind of solved some of these problems. I guess something to point out is even in some of the examples, the cut point has been 0.5, and these ones have 2, but it's not always 0.5. So you have to sort of figure out what that cut point is by plugging in these boundary values into the CDF. And then that will end up telling you what these cut points are. So we'll go through, so this is just the same stuff from the homework. So there's an example here. Happy to go through that if that would be helpful. And then the other problem is if you have a square, we've already kind of talked about this, this x plus 1 squared, it could, this whole bowl is described by x plus 1 squared. But then the question when you're inverting is, do I take this portion or this portion? And that's where knowing where your outcomes are supposed to be is helpful. So I know my outcomes are supposed to be from -2 up through, whatever the 0. And I know that this parabolic outcomes are only supposed to be from -1 to 0. So I better choose my inverse so that I select for those outcomes. So when I do the inverting process in this square root, I chose a plus because I knew my outcomes went from -1 and higher. They didn't go from -1 to lower. So that's why I chose a plus. So any questions about any of those? Otherwise, moving forward here, it's just, I just go back through, make sure you're comfortable with, what do I mean by stochasticity? How does that involve randomness? Know the definitions of these things that show up in ARENA: entities, attributes, resources, state variables. Know how to do a hand simulation. Now that we've gotten to ARENA, I added this little image here. There's a step inside of ARENA next to the play button, and that actually is moving through the internal event calendar that ARENA calculates. And so if you're ever running through ARENA and you effectively have a timeline of events that ARENA has figured out, and every time you hit step, it's doing what you do in the hand simulation. So make sure you're comfortable with looking at these. Make sure you know those activities and how these are activities and how those both differ from these delays. Probability, know several distributions, know the rough properties of these distributions and when you would use them. Know the rough properties of these distributions and know when you would use them. Know that a Poisson counting process, how it relates to both an exponential and a Poisson. And then the random variate stuff, which is what we kind of covered in the first half. Any other final questions? Any other questions come up? Feel free to use the discussion board. That way everybody else can see the answers, or you can email me or the teammates directly. Let's do an attendance question then. So we'll get to one of those slides. Yeah, know the runs test. Even though you didn't do it on homework. Know which one of these is a CDF, which one of these is a PDF, and so on. And so for your attendance question, let's say, should you bring a pen to the exam? That is the attendance question. The answer is no.